All right, so now I'll try to go back to this. All right, we're going to start with the definition of a sequence. A sequence is a list of numbers in a particular order. No. In a particular order. A list of numbers like 1/2, 2/3, 3/4, 4/5, ... That would be a sequence of numbers. They're in a particular order. This is the first term, and it's usually called a sub 1. The second term would be a sub 2. The third term is a sub 3. The fourth term would be a sub 4. The general term would be a sub n. And the sequence of numbers would usually go on forever. We're usually talking about an infinite sequence of numbers. All right, there's general notation. There's ways to list a sequence of numbers. You can list it with general notation, where you just have a sub n in here. Or you may have a sub n as n goes from 1 to infinity. Or you may just have these all listed individually. So this is kind of the notation. A sequence does not have to start at 1, but it usually does. Okay, it does not have to start at 1. No. It'll always be a positive. N will be a positive integer. 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 like that. Okay, if you look, instead of me writing all this out, if you look right here, they give you an example of different sequences, and then they show you 3 different ways to write that same sequence. For instance, this particular sequence is the sequence of numbers of the form n over n plus 1, where n goes from 1 to infinity. Or you could write it as just the general term, where a sub n is equal to n over n plus 1. Or it can be a list of numbers, where they let n be 1. And if you let n be 1, then you get the fraction 1 over 2. If you let n be 2, then you get the fraction 2 over 3. Do you see how they get each term? When they let n be 4, then this would be 4 over 5. This sequence, here's one way to write it, here's another way to write it, and then here's a list of numbers. So there's different ways to start. Notice this sequence does not start at 1. It starts at 3. So your first term is a sub 3 in this one. Yes?
So the question I have,
Yes.
would this be like, don't we have to memorize these like formula or something?
No, you're not going to memorize the formula. No.
They're just showing ways you can achieve.
They're just showing you 3 different ways that you can talk about a sequence of numbers. And usually you're going to see a sequence listed as this one right here, or this one right here. Sometimes it'll be listed like this, and you have to find this formula right here. Okay? And sometimes it's listed, pardon?
Like how you achieve it.
Right, how do you get, yeah. What is the general term? If they give you a list of numbers, can you tell me how to find the 100th term? Can you give me a formula for that? Or, like if this one, if they give you this, can you tell me what the 100th term is? And you would say,
It's always gonna be one more than what it
well, for this particular one, yes. So let's look at some of those problems where we're doing that kind of thing. Number 3. We've got some problems that we would look at. Problem number 3, they say a sub n is 2 to the nth power over 2n plus 1, and they want me to list the first 5 terms. This is number 3. If I have to list the first 5 terms, then I'm looking for a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5, the first 5 terms of the sequence. So all you do, n is 1 in this case, so this would be 2 over 2 plus 1, which would be 3. For this one, n is 2, so this would be 2 to the second power over 2 times 2 plus 1, and that would be, what, 4 over 5. For the third term, that means n is 3, so that would be 2 to the third power over 2 times 3 plus 1, so that would be 8 over 7, I believe. For a sub 4, that means n is 4, so that's 2 to the 4th power over 2 times 4 plus 1, which would be 16 over 9. And then for the a sub 5, n is 5, so that's 2 to the 5th power over 2 times 5 plus 1, so I guess that would be 32 over 11. Okay, so the first 5 terms, and then the pattern would keep going, but they're only asking for the first 5 terms.
Say they throw some, like on something crazy like 8 to 20, and then when you do 85, you just go to 25 and 20 or something.
Yeah, if they just ask you to find a sub 20, then that just means n is 20. So you just go up here, and that would be 2 to the 20th. Just substitute it in. 2 to the 20th over 2 times 20 plus 1. And that's why you have a general form, so you could go to the 20th term. Okay? So whatever that is what that
But what
20.
I had to know is like,
sorry.
they did go like we did 5 places on that one. What would we go from 20 to 25?
Oh, yeah, but they're not going to ask you that. They're just going to say list the first 5 terms, or 5 or 6 terms. Okay. In this particular case, this formula only depends on what n is. There is a type of sequence called a recursive sequence where each term is based on the term in front of it. An example of that would be like problem number 9, where the formula is given. A sub 1 is given to you as the number 1, and every term after that, a sub n plus 1, is 5 times a sub n minus 3. Each term is based on the one in front of it. It is called recursive. So let me show you how to find the 5 terms for this one. They give you the first term. The first term is 1. That's a given. To find the second term, to find a sub 2, this is a sub 1 plus 1. Using this formula, n is 1. So the formula says we need 5 times a sub 1 minus 3. A sub 1 is the term in front of us. So this is going to be 5 times 1 minus 3. 5 times 1 minus 3 is equal to 2. So this one says that a sub 2 is the number 2. All right, to find a sub 3, this is a sub 2 plus 1. In this case, n is 2. So the formula says we need 5 times whatever a sub 2 is minus 3. A sub 2 is that number. So 5 times 2 minus 3, that would be 10 minus 3, which is 7. And now a sub 3 is 7. Are y'all following me?
Quick question.
Yes.
Whenever you got the 8, like your 8 to 2 right there, times 5, right there, again, 5, 8 to 2, right there. You can pretty much just remove the 8 and put a 2 there in its place.
And in the next one, I'm going to put the 7. I'm going to do 5 times 7 minus 3.
No, I'm talking
Right there? Yes, I can put, yes,
You can remove the 8 and put the number there.
yes. Well, no, I can't put a 2 there. The only thing I can put there is the term in front. It just so happens that a sub 2 is 2. A sub 2 might have been 10. And then that way I would put a 10 there.
I didn't mean.
Oh, I'm sorry.
Whenever you're doing the equals 5 times the 2 minus 3 right there. See, right?
That's-
Right.
yes.
When you do that, you just remove the 8 and move that number up. I'm talking about do your.
Are
do
you,
your whatever
which
it is.
2 are you talking about? Are you talking about this 2 or are you talking about this 2? They are two different 2s. No, 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 this is not the 2 I'm moving in there. The 2 I'm moving in there is the 2 from the problem in front of it. I'm moving this 2.
I got it. It was the 8 and 2, okay. That's
It's
probably
this
that.
2. It has nothing to do with that 2 except that it's telling you which term to get. And that term, not that number, that term.
But that's where I was confused at. I didn't know if you moved the 2 up or the 2 came.
No. The 2 came from the problem in front of it.
Okay.
So I think maybe you'll see it when I get to the next term, because when I do a sub 4, this is actually a sub 3 plus 1. So the formula says I'm doing 5 times whatever a sub 3 is minus 3. Well, what was a sub 3? What did we find a sub 3 to be? 7. So we're putting 5 times 7 minus 3, so that's 35 minus 3, which looks like it's 32. So my a sub 4 is 32. So I'm putting the term in front of it in the problem. So my next term for a sub 5 is going to be 5 times 32 minus 3, which is a big number. What is that? Did y'all get it, Peter? 157, thank you. So the next time I'd put 157 in there. So I've got the terms, first few terms are 1, 2, 7, 32, and 157, and the pattern continues. That is recursive. It's based on the term in front of it. Do I need to do another one like that? Everybody got it? Okay. All right, then you get down to problems like number 14, where they give you a list of numbers. That's a 4, that's 64. And they are asking us to find the formula, find the general term. What is a sub n? This is where you have to look for patterns. And some people are better at this than others. I'm not particularly good at it. I can usually figure something out. But
Like -4 there.
you've got to find the pattern, you know. This is your first term, this is your second term, your third one, your fourth one, your fifth one. It's based on an n, and n has got to be in there somewhere. So the n is 1 here, n is 2, n is 3, n is 4, n is 5. So first thing I notice that this is what we call alternating, because the terms are alternating between positives and negatives. Positive, negative, positive, negative, positive. So somewhere in here is going to be a -1 to a power. So I usually go ahead and take care of that first. All right, I have a -1 to some power. I need it to be positive here on the odd numbers, and I need it to be negative on the even numbers. So it's not -1 to the nth power, but it might be, what, -1 to the n minus 1 maybe? Because 1 minus 1 is going to make that a positive. 2 minus 1 is going to make that -1 to the first, which is -1. So I got -1, and then I got to figure out the rest. I've got 4, -1, 1/4, 1/16, -1/16, 1/64. Do y'all see anything in there that's looking like a pattern to you? Okay. Negative times 1/4, but no, we're going to do something with this. How do we get it to be a 4? And like this is 4 in the denominator. This is 4 to the first power. This is 4 to the second. This is 4 to the first. This is 4 to the second. This is 4 to the third. The next one's going to have a denominator of 4 to the fourth, 4 to the fifth. So what can we do? How is that related to this n power? Or to this n? N is 3, but I have a 1 down here. N is 4, I have a 2 down here. N is 5, I have a 3 down here. Would maybe n minus 2? Okay. Does that work then when we get down here to the 4 and the negative 1? If n is 1, then this makes this 1/4 to the negative 1 power. 1/4 to the negative 4 is 4. So that works. Does it work when n is 2? When n is 2, you have 1/4 to the 0 power, and that's 1. So it looks like this is a formula for the general term, and it would work for all of those terms right here. I've got my negative 1 right there.
You're not using that whole thing. It's just like pretty much.
If n is 1, then this is going to be negative 1 to the 1 minus 1 power times 1/4 to the 1 minus 2 power. 1 minus 1 is 0, so that makes that a positive 1, and this makes this 1/4 to the negative 1 power, which gives me a positive 4, and that's what I needed right there. So it works for that one, and it'll work for the next one.
Because if we put a 2 over there, it's negative 1. Like the 2 minus 1, it makes that the 1 power, which is the same thing.
When n is 2, is that what you're talking about? When n is 2, then I have negative 1 to the 2 minus 1 power, and I have 1/4 to the, where's my formula? To the 2 minus 2 power. Well, this is going to be negative 1 to the first power, which is negative 1, and 1/4 to the 0 power is 1, so here's my negative 1. So this makes my pattern. This is not the only formula, it is a formula that works for every term in there. All right, let's look at another one. Maybe number, let's try number, I don't know, number 16. It's got 5, 8, 11, 14, 17. Remember, n is 1 here, n is 2 here, n is 3, n is 4, n is 5. We have to find some kind of pattern that will work and give us each of these numbers. No negative, they're always positive, so I don't have to, they're not alternating. Anybody see anything?
It's all shifting by 3. It increases by 3.
Every time it's increasing by 3, but what does that have to do with the n? Somehow we got to get an n in our formula because n is 1, n is 2, n is 3, n is 4, n is 5. We could make it recursive. Let's see if that works. Are you going to define a sub 1 to be? If you do that, wait. Now, what did you say? A sub n is n plus 3 if we know, can't do n plus 3 because n would be 1, but we could do, if you defined the first term to be 5, let's see, would that work? If you say the first term is 5, then a sub n plus 1, how can we get that? Are you saying that could be a sub n plus 3? Does that work? So if n is 1, right here, then this is a sub, then that would be a sub 1 plus 3, which would be 5 plus 3, which would be 8. When n is 2, then that would be a sub 3 would be a sub 2, which we found to be 8, 8 plus 3, we could make it recursive, yes. You can make it recursive based on the 5, because every term we'd add 3 after that. There's also, I'm not sure if WebAssign is going to want a recursive. It's a good question. If they don't, can you think of another way we could write this formula, A sub n? That's not recursive. Let's see. Nope. Wait a minute.
That would work. That'll make it, the first one
I
would
don't
be
know. Is that going to work?
3 plus 2 is 5, then you use 2, and 3 times 2 is 6, plus 2 is 8. That would work.
I don't know that. Does that work? 1 is 5. A sub 3 is 3 times 3, which is 9, plus 2, which is 11. Yeah, that does work. So you could define it to be 3n plus 2. Well, it's like, sometimes you just have to make a stab at it. Just make a wild guess. All right, let's try one more. 1/2. Negative 4/3. 9/4. Negative 16/5. 25 over 6. Does anybody know what the next term's going to be? It's not listed. The next one would be negative 36 over 7, right? And 49 over 8. So how was the pattern for that? I mean, in ends. All right, this is 1 squared, this is 2 squared, this is 3 squared, 4, 5, 6 squared. So that is n squared. And then what'd you say was on the bottom? You add 1. You would have n plus 1. All right, and then the negative, you've got to take care of that. So that would be negative 1 to the n minus 1 maybe. And that's a formula for that also. Okay. Still sort of halfway with me? All right. One thing we're interested in with sequences of numbers is we are interested in whether or not these sequences of numbers are getting larger and larger and larger as time goes on, or are they getting smaller and smaller and smaller, or are they actually getting closer and closer and closer to another number? For instance, this sequence of numbers, you could probably make a guess. 5, 8, 11, 14, 17, blah, 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 blah. This sequence of number is increasing, and every term is going to be increasing. It's not approaching anything at all, right? You plot those, if you plotted these numbers on a number line, you would just be getting bigger and bigger numbers. So it's approaching infinity. All right, but what about a sequence of numbers like this one? 1/2, 2/3, 3/4, 4/5. If you plotted, let's say you have 0 and you have a 1 here. If you looked at the sequence of numbers, the first one is 1/2. Then it's 2/3. Then it's 3/4. Then it's 4/5. The next one is going to be probably 5, 6, 7, 8, 9, 10, 9 over 10, 10 over 11. This sequence of numbers is actually not getting bigger and bigger and bigger. In fact, it will never get over 1. That sequence of numbers is actually approaching the number 1. So these fractions are getting closer and closer to 1. So that is what we're talking about when we talk about a limit. Now you can take, I pulled these pictures out of your book, and I don't know if you can see. This is the sequence of numbers defined by n over n plus 1. They plotted these on a number line, and you can see that this sequence, as n gets bigger, these numbers are getting closer and closer to 1. Another way to graph these numbers is to put them on a graph like so. Whoa, on an n a sub n chart. The first term is 1/2. The second term is 2/3. The third term is 3/4. The fourth one is 4/5. The seventh one is 7/8. And you can see with these dots, if you connected them or if you look at them, it's approaching this 1 right here.
It gets right up to it, but it don't actually cross it.
Right, and it'll never touch it. It just keeps getting closer and closer to it. So we say that this series is approaching 1, and that implies a limit. So we would say the limit as n approaches infinity of this sequence is 1, because it's getting closer and closer to this 1. Our n's are getting bigger and bigger and bigger. We have no restriction on what our n's are, what numbers we can put in here. I could put the number 1 million in here, and I would still not get to 1, but I'd get really close to 1. Okay. This one over here, this one right here, where I have 5, 8, 11, 14, 17, that limit as n approaches infinity of that sequence, it's approaching infinity because those numbers are getting bigger and bigger and bigger.
That was the question. So what do you do differently when you know it's not like approaching a number, it's just going to keep getting bigger and bigger, equal to infinity?
It's approaching infinity, or actually the limit does not exist. It's just getting larger and larger and larger. Larger and larger and larger. Okay, so if you are going to be asked in your homework to calculate like the first 10 terms of a sequence and then plot those decimals, they're going to be probably decimals on a graph, and see if it looks like your sequence is approaching a limit. Would y'all be okay with that, or do I need to kind of go through one?
If you come out like just a minute ago when you had on that printed out piece of paper.
Yes, yes. You'll be asked to find the terms, plot them, and see if it's approaching a number.
That won't be bad.
Okay. Keep in mind, I don't think you'll have any like this, but keep in mind that the dots can go up and then come down, and it still is approaching this line, whatever this line happens to be, whether it's 1 or 3 or 4. This would be the limit that it's approaching. Okay, it doesn't have to always stay below it. And this sequence of numbers is going up and down and up and down and up and down, but there's gradually closing in on that limit from above and below, so it's still approaching that limit. So I'm going to let you guys try some problems like that. Now, if this sequence is approaching a limit, we say that the sequence converges. It converges, and we say it converges to L, whatever that line is. If the sequence of numbers is getting bigger and bigger and bigger, or smaller and smaller and smaller, then we say it diverges. It is not approaching any particular number. It could also diverge by simply going up, down, up, down, up, down, up, down, up, down, and never getting closer and closer and closer to anything.
What about the end? If like it starts off really close and just keeps getting bigger and bigger apart, like one up here, but
Right.
instead of getting like backwards, it's closer at the beginning, but it gets bigger.
Then that would be a divergent, because it could be going here, 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 like that.
Right.
And that would be divergent because it's getting bigger this way and smaller this way, so it still is diverging, but it's diverging in two different directions. But those numbers are not approaching anything.
So that the first period being convergent as well, because
This is convergent, this is convergent. These two down here are divergent because they're not approaching anything. Okay? Now, you're going to be asked to tell whether a sequence converges or diverges. To do that, you're going to take a limit. Okay? So, if you are given number 23, where a sub n is 3 plus 5 over n squared, n plus n squared, and they want to know if it converges or diverges. That's the question. If it converges, find the limit. Well, the easiest way to tell convergence and divergence is to take a limit. So think of this as a function. 3 plus 5x squared over x plus x squared. If you think of this as a function, then you're going to take the limit just like you did in Cal 1. Your limit rules still apply, and the limit rules that you need to go back over, these are the same ones they had in Cal 1. The limit rules are right here, 737, right at the bottom of this page. Okay? These limit laws are the same thing you had in Cal 1. Pardon? Page 737. They apply to sequences just like they apply to functions. Now, when you take a limit to see if it converges or diverges, you can look at the limit. I usually just stick with n's as n approaches infinity of 3 plus 5 n squared over n plus n squared. When you calculate a limit at infinity, where you have polynomials on top and bottom, what you do is divide by the highest power of your variable that's in the denominator to do this limit. N squared is what you're going to divide by. So you divide every term, 3 divided by n squared, plus 5 n squared divided by n squared, sorry. 5 n squared divided by n squared, n divided by n squared, and n squared divided by n squared. So this is the limit as n approaches infinity. 3 divided by n squared plus 5 over 1 over n plus 1. Okay. This is now in a form that you can calculate the limit. As n approaches infinity, what is happening to this fraction right here? 3 divided by n squared. The denominator is getting larger and larger and larger, so this is going to 0. In the denominator, this 5 is not affected by your n's getting bigger. In the denominator, 1 divided by n. N is getting larger and larger and larger. Your fraction is going to 0. The limit of this sequence is 5. So this sequence converges, and it is converging to 5. It converges, and it converges to 5.
So, asking if you were to put that in the calculator, set that up, would it be like each one do the same thing pretty much to it? Or not? This doesn't need to be hand done?
These need to be hand done because when you get later in the chapter, if you can't do this right now by hand, you won't be able to do anything we do later in the chapter. One of those words of caution that Tori was talking about, it's in the details. Okay? So please try to do these by hand now so you can do the harder stuff later. Okay? You can double check yourself in your calculators if you want to. All right, what about this one, number 25? A sub n is n to the 4th over n to the 3rd minus 2n. And they want to know if this sequence converges or diverges. We're going to treat it like a function and take a limit. The limit as n approaches infinity. You have n to the 4th over n to the 3rd minus 2n. limit at infinity. You take the highest power of n in the denominator and divide everything by it. And don't forget your notation. The limit as n approaches infinity. The highest power in the denominator is n to the third. So I have n to the fourth over n to the third. N to the third over n to the third to n over n to the third. So that is the limit as n approaches infinity. On the top, that simplifies to an n. On the bottom, this is 1 minus 2 over n squared. In the denominator, 2 divided by n squared. This goes to 0. Yes, so the whole fraction goes to 0. But now all you're left with is n over 1, and as n gets larger and larger and larger, this term gets larger and larger and larger, so this approaches infinity. These terms are getting larger and larger and larger, so this sequence diverges. The limit is infinite. Okay, here's one, and I need to give you this one because I need to tell you the theorem that goes with this one. If a sub n is equal to negative 1 to the nth power, this is 35. 2 times the square root of n. All right, there's a theorem. Everything, these terms right here have all been positive. There's no negative in either of these terms. They're positives. These terms are going to be alternating. To decide if this one converges or diverges, there is a theorem that says if the limit as n approaches infinity of the absolute value of a sub n approaches 0. If that limit is equal to 0, then the limit as n approaches infinity of a sub n is going to be 0, and the sequence will converge. And that theorem is Theorem 6 on page 738. So if we have what we call alternating with this negative 1, all we have to do is look at the absolute value of this one. The absolute value of this is the term 1 over 2 square roots of n. So look at the limit of this one. As n gets larger and larger and larger in this denominator, this fraction is getting closer and closer to 0. So this limit approaches 0, which implies that our sequence also goes to 0. So it implies that our sequence, negative 1 to the nth over 2 square roots of n, converges. And it converges to 0.
What happens if you do one that you actually get it? Like, you can say we produce this number, or there's never going to be any.
What did you say? That if what happens if this goes to another number?
If it's something other than, say something other than 0, it would be divergent.
This theorem really doesn't apply to anything other than zeros. But there would be cases where if it were like a 2 or a 3, then this would be going to a 2 or a 3 also on opposite sides. But the theorem is only good if it's approaching 0. Okay. All right, the other thing you have to be able to tell is whether a sequence is increasing or decreasing. Are the numbers in your sequence getting larger? Are the numbers in your sequence getting smaller? That is called a monotonic sequence. Monotonic means your sequence is either an increasing sequence or it is decreasing. Now, I know your intuition tells you what an increasing or decreasing sequence is, right? If it's increasing, then every term has got to be getting bigger and bigger than the one in front of it. Yeah, if it's decreasing, every term's got to be smaller and smaller than the one in front of it. All right, so if you're asked whether a sequence is monotonic, you're asked to tell, is it increasing or decreasing? Non-monotonic is neither. It's neither increasing nor decreasing. So we're going to do a problem with that in a second. But I also want to talk about whether a sequence is bounded. A sequence is bounded if it has an upper bound and a lower bound. Okay. If it has an upper bound, and you're thinking about plotting the points, okay? If it's got an upper bound, then as you plot the points, these dots are not going to go across, they're not going to get bigger than a certain point on your graph. Are y'all following me? That means it's got an upper bound. If it has a lower bound, that means these terms are not going to go below a certain point. It would have an upper bound and a lower bound. This makes a sequence bounded. Okay? Sometimes it may have only a lower bound. Okay, do you see that I just drew there? It has a lower bound. This is my lower bound. It has no upper bound. It is not bounded. Okay, following me? And the same could be true if it's got an upper bound but no lower bound, then it is still not bounded. It only has an upper bound but no lower bound. So if you're asked if a sequence is bounded, you have to check for an upper bound and a lower bound. Okay. Sine and cosine are bounded. Exactly. Because they have uppers and lowers. If your sequence is, this is another theorem. Let me show you where this theorem is. This theorem is on page 742. It's called the Monotonic Sequence Theorem, which says that every bounded monotonic sequence is convergent. Each bounded monotonic sequence converges. Alright, so if it's bounded, it's got an upper and a lower. If it's monotonic, it's either increasing or decreasing, but it's staying in those bounds. So if it's monotonic and it's bounded, then it's going to converge. Okay? So, some problems that you're going to have to decide. You're going to have to decide if your sequence is increasing, decreasing, and is it bounded. So let me just give you two examples of how I do these. And I'll look at number 73, I suppose. One over 2n plus 3. All right, there are several ways to tell if a sequence is increasing or decreasing. That's the first question I would answer. Is it increasing, decreasing, or neither? Okay? It is not okay, listen to me. It is not okay to pick two consecutive terms and look at them and see if one is bigger than the other. That is not okay. Because it might appear at the beginning of a sequence that it's either increasing or decreasing, but at the end, it may not be doing the same. So it is not okay to do that. To tell if something is increasing or decreasing, I personally think the best thing to do is to look at the first derivative. Treat it as a function. Do you remember your first derivative test from Cal 1 maybe? If the first derivative is positive, it's increasing. If the first derivative is negative, it is decreasing. So I think that's the easiest way. So that's one way. I would look at the first derivative.
That would be increasing.
The second thing I would do, if I didn't like the first derivative, then look at a sub n, compared it to a sub n plus 1, and use general terms. And I'll show you what I mean on either one of those, if you want me to. All right, I think you know I take a first derivative, so let me show you what I would do with this one. If you look at the nth term, you're looking at 1 over 2n plus 3. The n plus 1 term is 2 times n plus 1 plus 3. You put an n plus 1 where you have an n. And you can put a symbol, say you think this is an increasing function or decreasing. You think that's bigger, that's smaller than this one. These are positive numbers. There's no negatives here. All you have to do is cross multiply. Is 2n plus 1 plus 3, is that bigger than 2n plus 3? Well, if you can't tell, simplify this. This is 2n plus 2 plus 3. This says 2n plus 5. Is that bigger than 2n plus 3? Yes. 2n plus 5 is bigger than 2n plus 3. That says what? That means this term is smaller than this one. This is a decreasing function. Because a sub n is bigger than a sub n plus 1. If you don't like that method, this was method 2, then the derivative, you can do low-d-high on this one if you want to, it's a quotient, or you could write it as 2n plus 3 to the negative 1 power, if you take the derivative of that. Times 2. The derivative is negative 2 over 2n plus 3 squared. That derivative is less than 0, which says this is decreasing. I gave you 2 ways to tell decreasing. Do you like either of them? Like the derivative? I prefer the derivative myself. If you want to do low-d-high minus high-d-low over low squared, that's fine. Just take the derivative. All right, so it's decreasing. We've answered the first question. This is decreasing. All right, so the next thing we have to tell, is it bounded? Yes.
Where you put decreasing the an is greater than an plus 1. Which one are you calling the an? Where you did it?
This is an. This is an plus 1 because it has an n plus 1 in it. This is smaller. That means each term is getting smaller.
Right. I'm just trying to, you've got 2n plus 5, that one's going to be the n plus 1. Correct or am I incorrect? The 2n plus 5 is there less.
All right. This is what you're trying to, this shows your a sub n and your a sub n plus 1. This is just the algebra to prove this statement. So this is not where you look for your a sub n and your a sub n plus 1. This is your a sub n and your a sub n plus 1. So you have to look back at your original problem.
A lot of the denominator can get bigger and bigger, so the number gets smaller and smaller.
Correct. Correct. Same thing. And that's all this showed.
That's what I'm looking at.
Because this is not the n plus 1 term. This is the n plus 1 term is 1 over this. That's not the n plus 1 term. Can you say that? I would probably allow you to say that. But I need you to say something. Don't just say, it's decreasing. No, that's not legal. That's not legal. Because like I said, while the definition says that every term has got to be getting smaller than the one before it, that's not necessarily true. It can start off a certain way. Your sequence can start off a certain way, but then as it gets to the end, it's going to switch. And it's really what is it ultimately doing way out there that matters, not these first few terms. So you can't say the first term is this, the second term is this, so obviously it's decreasing. You can't do that. We mathematicians are kind of picky about stuff like that. Okay? We still hadn't answered the second part of the question. Is it bounded? All right, so if it is bounded, it has to have an upper bound and it has to have a lower bound, okay? Now think about this and do this logically. If this is decreasing, then the first term is probably the smallest one. I mean the largest one, because it's a decreasing function. So a sub 1, figure out what the first term is. Well, the first term is 1 over 2 plus 3. The first term is 1/5. All right, our function is decreasing. So now what we see, this is going to be the upper bound. Okay? To see if it has a lower bound, you look at the limit. What is this going to? As n gets larger and larger and larger, what are these fractions approaching? Well, what is this limit? As this denominator gets larger and larger and larger, this fraction is going to 0. So 0 is going to be your lower bound. It has an upper bound and a lower bound, so my sequence is bounded and it is therefore convergent. Upper bound is 1/5, the lower bound is 0. Every term is going to be between 1/5 and 0. We say it's bounded and it's convergent.
And it has to have both an upper and lower to be convergent.
It does. And that is a common mistake that I see. All right. People will say, yeah, it's got one bound, it's got an upper bound, so it has to be bounded. That's not the question. The question is, does it have an upper and a lower both? Yeah. Do you need to look at another one? Yes or no? Y'all good?